Hello and welcome to Linear Algebra. Welcome to educator.com. This is the first lesson of the Linear Algebra course here at educator.com. It is a complete linear algebra course from beginning to end. So linear algebra, I'm going to introduce just a couple of terms right now just to give you an idea of what it is that you can expect in this course. It is the study of something called linear mappings or linear transformations, also known as linear functions, between vector spaces. And this is a profoundly important part of mathematics because linear functions are the heart and soul of science and mathematics. Everything that you sort of enjoy in your world today consists of essentially a study of linear systems. So don't worry about what these terms mean, vector space, linear mapping, transformation, things like that. We'll get to that eventually. Today's topic, our first topic, is going to be linear systems. And it's going to be the most ubiquitous of the topics because we're going to use linear systems as our fundamental technique to deal with all of the other mathematical structures that we deal with. In one form or another, we're always going to be solving some set of linear equations. So having said that, welcome again. Let's get started. Okay, so let's just start with something that many of you have seen already. If not, no worries. If we have something like ax equals b, this is a linear equation. One reason that linear is used, the term linear, is because this is the equation of a straight line. However, as it turns out, although we use the term linear, because it comes from the straight line, later on in the course we're actually going to give a precise definition of what we mean by linear, and believe it or not, it actually has nothing to do with a straight line. It just so happens that the equation, this ax equals b, which can be represented by a straight line on a sheet of paper, on a two-dimensional surface, it happens to be a straight line, so we call it linear, but the idea of linearity is actually a deeper algebraic property about how this function actually behaves when we start moving from space to space. Okay, so this is sort of a single variable. We have ax equals b, something like, for example, I don't know, well, that's okay, we'll just leave it like that. If I can write this, a1x1 plus a2x2 plus a3x3 equals b. Well, these a's are just different coefficients, 5, 4, 6, negative 7. These x1, x2, and x3 are the variables. So now instead of just the one variable, some equation up here, we have three variables, x1, x2, x3. We can have any number of them, and b. So a solution to something like this is a series of x's that satisfy this particular equation. That's all that's going on here. A linear equation, what you know of as linear essentially is when this exponent up here is a 1. That pretty much is what we're used to seeing when we deal with linear equations. But again, linearity is a deeper algebraic property which we'll explore a little bit later in the class. And that's when linear algebra becomes very, very exciting. Okay, so let's use a specific example. So if I had something like 6x1 minus 3x2 plus 4x3 equals minus 13, I might have something like x1 equals 2, x2 equals 3, and x3 equals minus 4. Well, this 2, this 3, this minus 4 for x1, x2, and x3 is a solution to this linear equation. That's it. We're just looking, that's all we're looking for. We're looking for variables that satisfy this equality. That's all that's happening here. Note, however, that we can also have x1 equals 3, x2 equals 1, and x3 equals minus 7. So if we put 3, 1, minus 7 in for x1, x2, and x3 respectively, we also get this equality, minus 13. So as it turns out, these particular variables don't necessarily have to be unique. Sometimes they can be unique, other times a whole bunch of set of numbers can actually satisfy that equality. So we want to find as many of the solutions that satisfy that equality. Okay, now let's generalize it some more and talk about a system of equations. So I'm going to go ahead and represent this symbolically. So let's see, we have a11 x1 plus a12 x2 plus dot 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 plus a1n x sub n equals b sub 1. So this just says our first equation, we have n variables, that's what the x1 to xn, and these are just the coefficients in front of those variables x's, and this is just some number. So this is one linear equation. And now we'll write another one, a21 x1, and I'll explain what these subscripts mean in just a moment, plus a22 x2 plus dot 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 plus a2n x sub n equals b2. Now we have our second equation. And then we go down the line. So I'm going to put a dot 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 there, dot dot dot. That means we're dealing with several equations here. And then I'm going to write a m1 x1 plus a m2 x2 plus dot 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 plus a mn, I know that's a little small, but that's an mn right there, equals b sub m. So notice we use two subscripts here. Like for example, we usually call the subscripts ij, and the first subscript represents the row or the equation. So in this case, 1, 2, 3, 4, 5, all the way to the mth equation. So a11 is the first equation, and the second entry, j, represents that particular column, that particular entry. So a11 represents the first coefficient in the first equation. If I did something like, let's say I had a32, that would mean the third equation, the second entry, the second coefficient, the coefficient for x2. That's all this means. So here I have, notice x all the way to n, xn, xn, all the way down. Oops, I forgot an xn right here. So I have n variables, and I have as many rows, m equations. And this is exactly what we say. When we have m equations in n variables, this many, and this many, we just arrange it like this. So this is a system of linear equations. What this means when we're looking for a solution to a system of linear equations, as opposed to just one linear equation, we're looking for, we want a set of x1, x2, all the way to xn, such that all of these equations are satisfied simultaneously, such that all equalities, I'll say equalities instead of equations. We know we're dealing with equations. We want all of these equalities to be satisfied simultaneously. In other words, we want numbers such that that holds, that holds, that holds, that holds. If one of them doesn't hold, it's not a solution. Let's say you have 7 equations, and let's say you found some numbers that satisfy 6 of them, but they don't satisfy the 7th. That solution doesn't have that system doesn't have that solution. It has to satisfy all of them. That's the whole idea. Okay. Let's see what we've got here. Okay. We're going to use a process called elimination. To solve systems of linear equations. So now we're going to start in with the examples to see what kind of situations we can actually come up with. One solution, infinitely many solutions, no solutions. What are the things that could happen when dealing with a linear system? how many variables, how many equations, and what's the relationship that exists, just to get a sense of what's going on, just to get us back into the habit of working with these. Now, of course, many of you have dealt with these in algebra. You've seen the method of elimination. You've used the method of substitution. Essentially, elimination is turning one equation. Let's say you have two equations and two unknowns. You're going to manipulate one of the equations so that you can eliminate one of the variables, because again, in algebra, ultimately, when you're solving an equation, you can deal with one variable at a time. So let's just jump in, and I think the technique itself will be self-explanatory. Okay, so our first example is x plus 2y equals 8, 3x minus 4y equals 4. We want to find x and y such that both of these hold simultaneously. Okay, so in this particular case, elimination, and it really doesn't matter which variable you eliminate. So a lot of times it's a question of personal choice. Some people just like one particular variable. Oftentimes you'll look at what's, what looks like it's easy to do. That'll guide your choice. In this particular case, I notice that this coefficient is 1. So chances are if I multiply this by 3, negative 3, this whole equation by negative 3 to transform it, and then add it to this equation, the negative 3x and the 3x will disappear. So let's go ahead and do that. So let's go ahead and multiply everything by negative 3. And when I do that, I tend to put a negative 3 here, negative 3 there to remind me. So what this ends up being is minus 3x minus 6y equals negative 24. And of course, this equation, we just leave it alone. We don't need to make any changes to it. 3x minus 4y equals 4. And now we can go ahead and add them. The minus 3x plus 3x, that goes away. Minus 6y minus 4y gives us minus 10y. Minus 24 plus 4 is minus 20. And when we divide through by minus 10, we get y equals 2. So we're able to find our first variable, y equals 2. Now I can put this y equals 2 back into any one of the original equations. You could put them in these two. It's not a problem. Multiplying by a constant doesn't change the nature of the equation. Because again, you're retaining the equality. You're doing the same thing to both sides. So y equals 2. Let's go ahead and use the first equation. Therefore, I'll go ahead and draw a little line here. We'll say x plus 2 times 2, which is y, equals 8. X plus 4 equals 8. Let's put the x on the left-hand side. X equals 4. So there you have it. A solution, x equals 4, y equals 2. If x equals 4, if y equals 2, that will solve both of these simultaneously. Both of these equalities will be satisfied. So in this particular case, we have one solution. Let me do this in red. So, one solution. Okay. Now let's try x minus 3y equals negative 7, 2x minus 6y equals 7. So let's see what happens here. Well, in this particular case, again, I notice that I have a 2 and a coefficient of 1, so I'm going to go ahead and eliminate the x again. So in order to eliminate the x, I need this to be a minus 2x, so I'm going to multiply everything by minus 2 up top. So minus 2 times x is minus 2x, minus 2 times minus 3y is plus 6y, equals minus 2 times minus 7 gives us 14. I can pretty much guarantee you that in your, just a small digression, the biggest problem in linear algebra is not going to be the linear algebra, it's going to be the arithmetic. Just keeping track of the negative signs, the positive signs, and just the arithmetic, addition, subtraction, multiplication, and division. So my recommendation, of course, is you can certainly do this by hand, and it's not a problem, but at some point you're going to want to start to use the mathematical software, things like Maple, MathCAD, Mathematica, they make life much, much easier. Now, obviously, you want to understand what's going on with the mathematics, but now as we get into the course, a lot of the computational procedures are going to be kind of tedious in the sense that they're easy, except they're arithmetically heavy, so they're going to take time. So you might want to avail yourself of the mathematical software. Okay, let's continue on. And then this one doesn't change, so it's 2x minus 6y equals 7. And then when we add these, we get plus 6y and minus 6y. Wow, these cancel too. So we end up with 0 equals 14 plus 7 is 21. We get something like this. 0 equals 21. Well, 0 does not equal 21. Okay? So this is no solution. We call this an inconsistent system. So anytime you see something that is not true, that tells you that there's no solution. In other words, there's no way for me to pick an x and a y that will satisfy both of these equalities simultaneously. It's not possible. No solution, also called inconsistent. Okay. Example 3. Okay, now we've got 3 equations and 3 unknowns, x, y, z. Well, we deal with these 2 equations at a time. So let's go ahead. We see an x here and a 2, a 3. So I'm going to go ahead and just deal with the first 2 equations, and I'm going to multiply. I'm going to go ahead and eliminate the x. So I'm going to multiply by a negative 2 here. And again, just be very, very systematic in what you do. Write everything down. The biggest problem that I've seen with my students is that they want to do things in their head and they want to skip steps. Well, when you're dealing with multiple steps, let's say if you have a 7-step problem and each one of those steps requires maybe 3 or 4 steps, if you skip a step in each sub-portion of the problem, you've skipped about 7 steps. I promise you, if there's been a mistake, which there always will be when it comes to arithmetic, you're going to have a very hard time finding where you went wrong. So just write everything down. That's the best thing to do. You'll never, ever go wrong if you write everything down. And yes, I'm guilty of that myself. Okay, so this becomes, let's write it over here, minus 2x minus 4y minus 2 plus 3z is minus 6z. Minus 2 times 6 is minus 12. And let's bring this equation over unchanged. That's the whole idea. 2x minus 3y plus 2z equals 14. Let's go ahead and, so the x's eliminate, and then we end up with minus 4y minus 3y is minus 7y. Minus 6z plus 2z is minus 4z. And minus 12 plus 14 equals 2. So that's our first equation. And now we've reduced these two, eliminated the x. So now we have an equation in 2 unknowns. So now let's deal with the first and the third. So in this particular case, I'm going to, let me do this one in blue. I want to eliminate the x again because I eliminated the x here. So I'm going to eliminate the x here. So I'm going to multiply by a negative 3 this time. So when I do that, I end up with negative 3x negative 3 times positive 2 is negative 6y. Negative 3 times 3 is minus 9z. And minus 3 times 6 is minus 18. And I'm hoping that you're going to confirm my arithmetic here. And then again, I leave this third one unchanged. 3x plus y minus z equals minus 2. I eliminate those. Minus 6y plus 1y is minus 5y. And then I get minus 9 minus 1 is minus 10z. Minus 18 minus 2, I get minus 20. So now I have my second equation. And this one was my first equation. So now I have 2 equations in 2 variables, y and z, y and z. Now I can work with these 2. So let me go ahead and bring them over and rewrite them. Minus 7y minus 4z equals 2, and minus 5y minus 10z equals minus 20. Good. So now we have a little bit of a choice to make. Do we eliminate the y or do we eliminate the z? Now, Again, it's a personal choice. I'm going to go ahead and eliminate the y for no other reason than I'm just going to work from left to right. Not a problem. So I'm going to multiply. So I need the y's to disappear, and they're both negative. So I think I'm going to multiply the top equation by a negative 5. And I'm going to multiply the bottom equation. I'll write that in black. No, actually, I'll keep it in blue. The bottom equation by 7. So I'll lose 7 here, 7 here. So this will give me a positive value here and a negative value here. That should take care of it. So let me multiply the first one. What I get is 35y, right? Negative 5 times negative 4 is plus 20z. Negative 5 times 2 equals negative 10. 7 times a negative 5 is negative 35y. So far, so good. 7 times a negative 10 is negative 70z. And 7 times a negative 20 is negative 140. So now, when we solve this, the y's go away, and we get plus 20z minus 70z for a total of minus 50z equals minus 10 minus 140 minus 150. That means z is equal to 3. Okay, so now that I have z equals 3, I can go back and put it into one of these equations to find y. So let me go ahead and use the first equation. So let me move over here next. I write minus 7y minus 4 times z, which was 3, equals 2. I get minus 7y minus 12 equals 2. Minus 7y equals 14. Y equals minus 2. Notice I didn't skip any steps. I wrote down everything. Yes, I know it's basic algebra, but it's always going to be the basic stuff that's going to slip you up. So y equals minus 2. If I've done my algebra correctly, my arithmetic, that's that one. Now that I have a z and I have a y, I can go back to any one of my original equations and solve for my x. Okay, I'm going to go ahead and take the first one simply because that coefficient is there. So I get x plus 2 times y, which is minus 2, plus, write it out exactly like that. Don't multiply this out, and make sure you actually see it like this again. Write it all out. Plus 3 times 3 equals 6. We get x minus 4 plus 9 equals 6. We get, oops, these little stray lines here. Erase these so you guys aren't bothered. Okay, x minus 4, what is minus 4 plus 9? That's 5, right? X plus 5 equals 6. We get x equals 1. And there you have it. You have x equals 1, y equals minus 2, z equals 3. 3 equations, 3 unknowns, and we have one solution. Again, one solution. And notice what we did. We picked 2 equations, eliminated a variable. The first and the third to eliminate the same variable. We dropped it down to now 2 equations and 2 unknowns. Now we eliminated the common variable, got down to 1, and then we worked our way backward. Very, very simple, very straightforward, nice and systematic. Again, nothing difficult, just a little long, that's all. Okay, let's see what else we have in store here. Example 4. Okay, so we have x plus 2y minus 3z equals minus 4. 2x plus y minus 3z equals 4. Notice in this case we have 2 equations and we have 3 unknowns. So let's see what's going to happen here. Well, this is a coefficient 1. This is 2. So let's multiply this by a negative 2. Let's go ahead and use a blue here. So we'll do minus 2 here, minus 2 there. And let's go, well, let's move over in this direction. So we have minus 2x minus 4y, and this is going to be plus 6z, right, equals positive 8. And then we leave this one alone because we want to eliminate the variable. 2x, excuse me, plus y minus 3z equals 4. Okay, let's eliminate those. And now we have minus 4y plus y should be minus 3y. 6z minus 3z is plus 3z. 8, 9, 10, 11, 12. That is equal to 12. Okay, so now we have minus 3y plus 3z equals 12. We can simplify this a little bit because every number here, all the coefficients are divisible by 3. So let me go ahead and rewrite this as, let me divide by minus, actually it doesn't really matter. So I'm going to divide by minus 3 just to make this a positive. So this becomes, let me actually do a little arrow. So divide by minus 3, this becomes a y, this becomes a minus z, and 12 divided by minus 3 becomes minus 4. Is that correct? Yes. So now we have this equation, y minus z equals 4. That's as far as we go. So now what we're going to do is, again, we need to find the solutions to this. So we need to find the x and the y and the z. So let's go ahead and solve for one of the variables. So y equals z minus 4. So now I have y equals z minus 4. And I have this thing I can solve for x. But what do I do with this? As it turns out, whenever I have something like this, z equals any real number. So basically, when you have a situation like this, you can put in any real number for z, and whatever number you get, let's say you choose the number 5. If you put 5 in for z, that makes 5 minus 4. Well, let's do that as an example. So if z equals 5, well, 5 minus 4 equals 1. That makes y equal to 1. And now I can go back and solve this equation. So let me just do this one quickly. We get x plus 2 times plus 2 minus 15 equals minus 4. 2 minus 15 is x minus 13 equals minus 4. That means x equals 4 plus 13 should be 9. So x equals 9. This is a particular solution, but it's a particular solution based on the fact that I chose z equal to 5. So notice, anytime you have two equations, three unknowns, more unknowns than equations, you're going to end up with an infinite number of possibilities depending on how you choose z. Z can be any real number. Once you choose z, you've specified y, and once you've specified y, you can go back and you specify x. So here we have an infinite number of solutions. Okay, so an infinite number of solutions is also another possibility. So we've seen one solution, a system that has one solution only. We've seen a system that had no solutions, it was inconsistent, and now we've seen a system that has an infinite number of solutions. Okay, let's see what else we can do here. We just want to be nice and example heavy, just to get us make sure that all the steps are covered, all the bases are covered, just so we know what we're dealing with. Okay, this particular system is x plus 2y equals 10, 2x minus 2y equals minus 4, 3x plus 5y equals 26. Okay, let's start off by eliminating the x here. So I'm going to multiply this by minus 2 to give us minus 2x minus 4y equals negative 20. And then, of course, this one stays the same. 2x minus 2y equals minus 4. When I do this, I get minus 6y equals minus 24. Y equals 4. Okay. So I get y equals 4. Now, notice I have three equations. So this y equals 4 deals with this first two. I need all three equations to be handled simultaneously. So now I can't just stop here and plug it back in. It's not going to work. I need to make sure. So now I've just done the first and the second. Now I'm going to do the first and the third. So this is first and second equations. Now I need to do the first and third. So now I'm going to, let me do this one in red. This is x, this is 3x, so I'm going to multiply by negative 3. So in this case, I have negative 3x minus 6y equals negative 3 times, let me actually cross these out, so negative 3 times that is negative 30. Let me make sure my negative signs work here. And I have 3x plus 5y equals 26. Now let's go ahead and do that. Okay, the 3x's cancel. Minus 6y plus 5y is a minus y. And minus 30 plus 26 is a minus 4. Divide by negative 1, so we get y equals 4. Okay, so notice, our first and second equation, we get y equals 4. Our first and third equation, we get y equals 4. These equations that we come up with, we've transformed this original system. Now, our original system has been transformed into x plus 2y equals 10, because that's what we're doing. We're just changing equations around. X plus 2y equals 10, and then we did this one. We got y equals 4, and we got y equals 4. Because it worked out the same, now I can take this y, put it in here, and solve for x. Let me make this a little clearer so it doesn't look like an x here. It is definitely a y. So now I take x plus 2 times y, which is 4, equals 10. So I get x plus 8 equals 10. I get x equal 2. And that's my solution. One solution. X equals 2. Y equals 4. So be very, very careful with this. Just because you end up eliminating an equation or eliminating a variable, in this particular case, notice we have 3 equations in 2 variables. You can eliminate a variable and end up with a y equals 4, but you can't stop there. You can't. You have to account for the third equation. So now you do the first and the third, and if there's consistency there, you end up with this system. This system is equivalent to this system. That's all you're doing. Every time you make the change, you're creating a new set of equations. You're just, now you're dealing with this system, and because this and this are the same, you're good. Now you can go back and solve for the x. Okay. So let's see what we have here. Again, we have a system of 3 equations in 2 unknowns, so we're going to treat it the same way. So let's start off by doing the first and second equation. So let me write first and second over here. So we're going to multiply this by negative 2, negative 2. So we're going to get negative 2x minus 4y equals negative 20. And this one we leave the same. 2x minus 2y equals minus 4. When we add, the x's cancel. We're left with minus 6y equals minus, and then we're left with y is equal to 4 again. So that's just the same thing that we had before. Now we'll take care of the first and third equation. This time let's multiply again by a 3. Let me do this one in blue. Negative 3, and we're left with, so the first equation becomes minus 3x minus 6y equals minus 30. And then this one becomes 3x plus 5y equals 20. So now, when I do this, the x's cancel. I'm left with minus y equals minus 30 plus 20 minus 10. I get y equal to 10. Y equals 4, y equals 10. There's no way to reconcile these two to make all 3 equalities satisfied simultaneously. So this is no solution. So again, just because you found a solution here, don't stop here. Don't just stop here and throw it into one of these equations because you just did it for the first 2. And certainly don't throw it into the third because that won't give you anything. No solution. These have to be consistent. First and second, this is first and third. Again, we're looking for this whole thing. What we just did here is the equivalent system that we've transformed it to is x plus 2y equals 10, y equals 4, y equals 10. There's your inconsistency. Okay, so all of these examples that we've done, it's always been the same thing. We see that we either have one solution, unique solution, we have no solution, or we have infinitely many solutions. Those are the only three possibilities for a linear system. One solution, no solution, or infinitely many solutions. Back in algebra, when we're dealing with lines, again, these are all just equations of lines, right? The ones in two variables, x plus y. Well, the no solution case, that's when you had parallel lines. They never meet. The one solution case was when you had, they meet at a point. And the infinitely many solutions is when one line is on top of another line. Infinitely many solutions. But again, we're using the word linear because we've dealt with lines before we developed the mathematical theory. Mathematics tends to work from the specific to the general. And in the process of going to the general, the language that they use to talk about the general is based on the stuff that we've dealt with in the specifics. We dealt with lines before we dealt with linear functions. Once we actually came up with a precise definition for a linear function, we said, let's call it, well, the ones who decided to give it a name said, let's call it a linear function, a linear map, a linear transformation. It actually has nothing to do with a straight line. It just so happens that the equation for a line happens to be a specific example of a linear function, but linearity itself is a deeper algebraic property which we'll explore and which is going to be the very heart of, well, linear algebra. Okay, let me just go over one more thing here. The method of elimination. So let's recap. Using the method of elimination, we can do three things essentially. We can interchange any two equations, and interchange just means switch the order. So if I have a particular equation that has a coefficient of 1 in one of the variables, it's usually a good idea to put that one on top, but maybe you prefer it in a different location. It just means switching the order of the equations. Nothing strange happening there. Multiply any equation by a non-zero constant, which is really what we did most of the time here. Multiply by a -3, -2, 5, 7, whatever you need to do in order to make the elimination of the variables happen. And then third, add a multiple of one equation to another, leaving the one you multiplied by a constant in its original form. So recall, when we had x plus 2y, we had x plus 2y equals 8, 3x minus 4y equals 4. When we multiply the first equation by -3, then added it to equation 2, we ended up with the following equivalent system. So we ended up converting this to minus 3x minus 6y and end up minus 24. And then we brought this one over, 3x minus 4y equals 4. Once we actually found the answer to this, which is, let's say, minus 10y equals minus 20, we ended up with a solution. Well, once we get that solution, this is now the new equation. So that's over here, y equals 2. But the original equation stays. So that's what we're doing when we do this. We're changing a system to an equivalent system. That's what we have to keep in mind when we're doing these eliminations. Notice the first equation is unchanged when we rewrite our entire system. Okay, thank you for joining us here at educator.com. First lesson for linear algebra. We look forward to seeing you again. Take care. Bye-bye.